Good evening, everyone, and welcome to this IAIS Dialogue. It is a great pleasure to introduce our today's speaker, Susan Stepney, Professor Emerita from Department of Computer Science at the University of York, and a Fellow of the International Academy of Information Studies. Susan has been one of the key figures in shaping unconventional and natural computation over past decades. Why does this matter beyond computer science? Because computation is about how systems transform information. Living systems do it, technical systems do it, social systems do it. And today, with AI technologies expanding explosively and consuming huge amounts of energy, the question is no longer whether computation matters. The question is how we can realize computation in more efficient, embodied, and materially grounded ways. I have known Susan for many years and have invited her to speak at several events in natural computing community since at least 2005, when she led the Grand Challenge for Computing Research Journeys in Non-Classical Computation. I have followed her work closely. What has consistently impressed me is her ability to combine conceptual depth with intellectual courage and deep knowledge of formalism, moving from formal methods to computation in chemical, physical, and other embodied systems. Today's talk on physical reservoir computing and embodied robot controllers continues that trajectory. Computation not as a software running on hardware, but as intrinsic dynamical process in material systems. I am very much looking forward to our discussion, especially in this IAIS dialogue format on how robot bodies themselves might become computational reservoirs. And the format today, as you might know, Susan will give a presentation, 30 minutes or half an hour, whatever it turns out, and then we follow by the discussion the rest of the time. We are two moderators, myself and Gordana Dodig-Crnkovic and Werner. So welcome, Susan, the stage is yours.
Thank you very much for that introduction. I'll now check that I can share my screen because I've got some slides to accompany this. And you can see the screen, I think. Is that correct?
Yeah.
Yes. Okay. I will carry on, and we'll see how this goes. So you notice that my title has a question mark at the end. This is very much due to being work in progress, thinking about actually how to do some of these things, bringing together some various ideas. So the inspiration for this idea comes from these two things. First of all, there's a fish in flowing water, appears to be swimming, but this fish is dead. And here we have a passive dynamic walker. There's a very slight slope, but this thing is walking down the slope. There is no power being provided to this system and no clear computation being provided to the system. So how can we use these ideas? Oh, sorry, the dead trout has stopped swimming and has gone on to something else, but let's move on then. So I'm going to give a little bit of an overview of physical reservoir computing and then talk a little bit about how this might be used as a robot controller, as an intrinsic robot controller. So to start with, I'm just going to talk about reservoir computing before we get into physical reservoir computing, just to give a little bit of background to people who might not have come across this before. And the model underlying reservoir computing, in particular the echo state network model, has this structure. We have a random recurrent neural network in the middle, I'm now going to try and be sophisticated and use a pointer. So here it's a random recurrent neural network. And as you know, recurrent neural networks are difficult to train normally because they have you have to do backpropagation through time and so on. But the reservoir computing gets around that problem. We have an input fed into the system through a linear weight matrix that then distributes that input into all the nodes in the internal recurrent neural network, which it can also itself be described by this weight matrix W. And then the state is read out from that through this output weight matrix, and then you get the output coming out, and we need the trained output from that. So let's see how that comes. That's the picture. Here's the maths, which isn't very difficult. We have the equation of the reservoir, which says that its state, its internal state at time t+1, and its internal state is simply the vector state of all its nodes, is, in the usual way, the weight matrix multiplied by its state at time t plus the input weight matrix multiplied by the state of the input. And then it's passed through this nonlinear function f. So that tells you the state of the network at the next time step. There's nothing magic going on there. The function f has to be some kind of nonlinear function. It might be tan h, sort of a sigmoid, or it might be ReLU, which is just 0 when things are negative and x when things are positive. And this is just a simple example of an open dynamical system. And by that it means that the state at t+1 is a function of the state at t and the input at t. It's open because it has inputs. And then the output value, v, at the time step v of t+1, is given by simply passing the state of the network through the output weight matrix. So far, so simple. Now, as I said, it's a random recurrent neural network, and it's random in that the network weight matrix W is itself a random weight matrix. So that just says that any node could be connected to any other node with any random weight, modulo some normalization condition to make sure things don't blow up, but I won't bother to go through that. Also, the input weight matrix here, the thing that takes the input and distributes it into the network, is also random. However, it can't all be random. We need something, and this output weight matrix, which is just a linear transformation of the internal state, is what is trained. But interestingly, it can be trained by a simple one-shot linear regression. It doesn't need backpropagation. It doesn't need backpropagation through time. It's a very straightforward training approach. So you don't train any of the weights inside here. You only train this output weight matrix. So what's interesting about that from a computational view? Well, one thing that's interesting about that is that you've got a very cheap way of training a recurrent neural network. And it was Herbert Jaeger who worked this out back in the early 2000s. But what's also interesting is that this weight matrix, the output weight matrix that you train, if you've got a different task, you can use the same reservoir and just supply a different output weight for a different task. So in some sense, you've got a computer here, but the program for the computer is this output weight matrix here. And I can just take that one out, slot a new one in, and I'm using exactly the same system to perform a different task. So we can think of this as the program. And what's going on inside, sort of an intuitive idea of what's going on inside, is that inside this recurrent neural network, you've got a load of nodes talking to a load of other nodes, and you've got a load of stuff going on inside. This is being kicked occasionally by this input So this is kicking. And if you think of this in some sense, the way I like to think of this is a sort of a mass of nonlinear jelly that's wobbling in an interesting way when it's being kicked from outside. And what wobbling in an interesting way means is that if you apply the correct linear transform to look at that internal state, you can see something interesting, something that you are interested in computing about the input, about the way it's being kicked. Now, as I said, this is the model, and this is how you would simulate it on a classical computer. However, this dynamical reservoir can be replaced by some physical material that has the correct properties. It doesn't have to be itself a random recurrent neural network at all. It can simply be some physical dynamical system that itself wobbles in an interesting way when you kick it. And there are lots of different materials that people have used for that. And the reason this works is because that the reservoir itself is a black box. It doesn't get trained, it doesn't change its weights, nothing needs to be done to it. So if you can provide some material that has the right kind of properties, you can use the material instead. You only need to train those external weights. So not only don't you need to manipulate the material, you don't need a detailed model of it or anything. It is literally a black box. And the only problem is it needs to have rich nonlinear dynamics so that it can wobble in an interesting way, and it needs to be excitable by that input stimulus. In other words, it wobbles when you kick it with the input stimulus. It needs to have an accessible, readable output state. So it can't be a completely black box. You do need to be able to put probes into the system so that you can read its state, so you can read how it's wobbling. And again, that single instance of that material can be configured into different reservoirs, very often just by applying sort of various electrical voltages or some other kind of configuration parameters to it, which does allow you to tune the material to be an even better reservoir than just having the initial lump of goo. And this is the thing that I think is fascinating about reservoir computing. It's not so much that you've got a quick and easy way to train a recurrent neural network. It's that you've got a quick and easy way to train some physical material that you would not necessarily think of being a computer to perform a computational task. And in fact, multiple different computational tasks. So one thing that I like to think of as potential is this rather nice quote from William James that I like to bring up in lots of times. This idea that the world depends on how we look at it. So the quote, other sculptors, other statues from the same stone, other minds, other worlds from the same monotonous and inexpressive chaos. And it says, my world is but one in a million, alike embedded, alike real to those who may abstract them. How different must be the worlds in the consciousness of ant, cuttlefish, or crab. And I've used this to draw this picture here. We could think of some large, complicated system that has inputs and outputs and so on. Maybe it's the entire world. And these little rectangles are potential output weight matrices that maybe have evolved, maybe have been learnt, who knows, but they are different ways of looking at the world, which is our reservoir, and we see different things. And so the ant, the cuttlefish, and the crab have got different output weight matrices from my output weight matrix, and so they see a different world. And this idea of being able to have different views of the world, I look at that, say that not only is this wobbling in an interesting way when you kick it, but these things are like little spectacles. You can actually use different spectacles and then you see different things. So that's the very simple, straightforward reservoir computing. what I need to talk about robots is to add a little extra bit to it, to have a feedback control mechanism, because I'm wanting to use these things in a feedback manner to control the robots themselves. So this is extremely simple diagram that you'll find in any textbook on control systems, classical feedback control system. You have some plants you're wanting to control, you've got some input to that plant, you've got some output from that plant, and then you tap off that output, feed it into some sort of controller, which you then use to modulate the input going into the plant so that it gets controlled to do the kind of operation you want. You know, anything from rolling a steel plate to the right thickness to flying a complex aircraft or a complex factory, controlling a complex factory. So let's see how this maps onto the ideas of reservoir computing. So we've got our feedback plant here. If we identify the plant with the reservoir and the output, so this Y here is V here. Sorry, I didn't have time to draw a diagram that had the right letters on, but this Y is the output. So we can add a feedback loop into our reservoir. We can take the output from the learnt system and feed it back through another input weight matrix, which you also have to train, into the system. And this looks very similar to this, where the output, the controller, is now this learnt feedback input, and the external input and this feedback input are combined. In this case, are just simply combined by being passed into this reservoir, which is the plant. So this feedback control reservoir, which is a standard thing in reservoir computing, maps very well onto the standard classical feedback control system. And I'll just put the maths up again. All that's changed is this new term here, where we have the output at time t going into the system through this feedback weight matrix. If there was no U, if there was no external, this would be now an autonomous dynamical system, a free running system, not open system, or just a completely self-controlling system. But if we've got both the input from the environment and the feedback from the system itself, we've got potentially a self-controlling open system. Obviously, to be self-controlling, it has to be, these matrices have to be trained correctly, but let's assume that we can do that. There are techniques for doing that. Right, finally, robots. And now we're getting question marks here. How can we take these ideas of physical reservoir computing and feedback control systems? Well, the argument runs like this. A physical reservoir computing exploits complex nonlinear materials to do computation. That's what physical reservoir computing does. And the material can be trained to compute many different outputs. In other words, it can perform many different tasks. So we need a complex nonlinear material. Well, a robot body is a complex nonlinear material. So in other words, a robot body can be exploited to compute. A robot body can be exploited as a physical reservoir computer. So it can be trained, it can be provided with the correct output weights to compute potentially many different outputs. And one of those outputs could be its own control function. So that output could be fed back in as its control function. Now, this isn't a new idea. This has been around for, I was going to say 10 years, but actually that's now 15 years, isn't it? Time does seem to go a little bit faster than is very pleasant. So people have been looking at this. Helmut Hauser, Kohei Nakajima, and one of Nakajima's students. I was going to say last year, but that's now 2 years ago. Have thought about this from a potential of more theoretical to start with, but this last one has actually implemented a system that does this to some degree. So if we wanted to do this, and again, these are still question marks because this is what we want to do. People have done it for relatively simple systems, but let's sit back and think about what we actually want for a robot that uses its own body as a physical reservoir computer to control its own actions at some level. So we need some sort of material body, maybe just a skeleton, that forms the structure of the body, and we need that. It provides stability, it provides leverage so that the system can actually move around. And that body has also got to support the sensors. It needs to have sensing of its environment, and also that body supports the actuators that enable those behaviors, especially higher level behaviors beyond just movement. It needs energy, which is used to power the body to produce the dynamics. Now, I showed the dead fish. The energy there was being provided by the flowing stream of water that the fish was in. And I showed the passive walker walking along. What you couldn't really see very easily was that it was slightly downhill. So the energy was being provided by converting its potential energy at the beginning into its kinetic energy of walking. But so you do need some external power source. We're not breaking any laws of thermodynamics doing this. Typically electrical power, but we've seen that other power sources are available. And then that energy source will often need to be distributed through the body. And actually having an energy storage in batteries is also quite useful, so that you don't have to provide the energy synchronously with the motion. And then information. Obviously, we're talking about computing here, not just physics. We need information in order for it to be able to guide it, to choose between potentially different behaviors. This information can be structured potentially hierarchically. The low-level reflexes are the main thing that I'm talking about with the physical reservoir computing. That's the kind of thing that it's really relatively straightforward to make the system do. But as soon as you get to higher level goals and planning, when you're having to switch between behaviors and decide which behaviors, you're probably going to need something a little higher level system there. But it will be interesting to see how much that you can use the robot body itself to provide. And again, that information needs to be transported around the body, maybe by some analog of another nervous system, so that the different parts of the body can be driven in different ways. And again, just like energy, the information needs to be stored in memory. It could be a centralized brain, it could be localized around the body, and even with physical reservoir computing, the physical reservoir has memory in it. So the body, just the configuration of the body has memory, and some of that can be exploited as well. It doesn't have to be RAM. Right, so here's some examples of the body skeleton, and there are at least three different ways that people think about this. So the first one is soft bodies. This is Kohei Nakajima's lab. They have a lot of work on octopuses. They started off with synthetic octopus arms to demonstrate that those could be reservoir computers. Then they used the same synthetic octopus arms, so they're sort of free-floating, sort of a synthetic arm, a silicone arm hanging and being wobbled. They demonstrated that that could be a reservoir computer, and then they demonstrated that it could be its own controller. So it could a feedback reservoir computer controlling itself. And their latest thing is this lovely thing. They call it a taco robot or something. I call it a quadrupus because it's like a four-legged octopus, and it can not very gracefully, but it can move itself. It can locomote itself by exploiting its own body as the computer, as the control feedback system to make it locomote itself, and that's quite fun to see that happen. However, of course, these continuous, pliable, highly nonlinear arms are quite easy to make, but they're difficult to construct into a system like this. They're difficult to monitor. You have to remember, I said you have to be able to extract the current state of the system to feed it into the output weight matrix. And they're a little bit difficult to actuate, because basically the only actuation that you've got is wobbling it backwards and forwards. It's quite fun because actually real octopuses can locomote underwater because you can push against the water, but they can also locomote on land as well. So that is quite interesting to see how this develops. So I'm watching Nakajima's lab with interest. Another approach people use is mass spring damper systems, where you have a bunch of nodes with springs between them and some damping to give you some nonlinearity. These are quite fun because you've got an analogous nonlinear ODE form of it, so you can easily build simulations of these things. You may need to add some rigid parts because these things do tend to flop and just collapse if you're not careful to brace them somehow. The thing I think of is quite interesting that we should be looking at more in these cases is tensegrity devices. And these are devices that are composed of a combination of rigid struts, which are in compression, and little cables which are under tension. And each of these nodes here between the thick struts and the thin cables has got a little motor on which can adjust the tension on the cable. And these things can, they don't collapse. They can be made to locomote, and they can be made to do various other things. If you can have inputs which actually act on the nodes or change the tension in the cables and things like that, and they can react to that, and they can be trained to have different behaviors. But like all of these things, I think that actually what we need to be doing is, once we've figured out what each of these kinds of components can do, is to have some kind of hybrid of these. And we've been suggesting a system that has a tensegrity spine. So it has a bunch of modules that are connected together using tensegrity devices that can then be used to move the spine, to sort of get various oscillations and so on in the spine, which are helpful for locomotion. But then you might want some mass spring damper systems to surround that spine to give you something more like musculature in a torso. And maybe you could add some soft body arms that could be like grippers or something like that that can actually also be used. So there's a lot of complexity in these systems, but we understand the individual components relatively well. But actually putting them together into a usable robot body is kind of the next step, I would say. These robots also need a rich sets of sensors. You need sensors for the external environment, but a lot of robotics assumes that all you need to sense is the external environment. But you also need a lot of sensors for internal proprioception, so that the system can actually measure and sense its own internal state. Now, I said with physical reservoir computing, you have to have access to the internal state because that's what gets fed into the trained weight matrix. So you need some way of accessing the internal state, and having a bunch of sensors in the body is really useful for that. Ordinary animals have got lots and lots of internal sensors so that they know how, you know whether you're standing up or lying down, you know whether, you can close your eyes and touch your nose with your hand and things like that. And again, it shouldn't be just single sets of sensors. We can have multimodal ones, so light input, sound input, pressure, so that it can sense if it's pressing against something. Magnetic sensors are actually useful for proximity and very useful for proprioception, because you can put magnetic sensors internally and read off whether one magnet is close to another one or not. Accelerometers are incredibly useful. The tensegrity devices We built one that had not just motors, but had accelerometers on the nodes, and we were using those accelerometers as the output for getting both get rotation, orientation, and acceleration, and so on. And so those are very useful for output, for sensing the internal state to then be used for output. Another interesting thing about physical reservoir computing and so on is these multimodal systems, inputs, can not just provide the sensing, but can provide some of the energy for driving the system. So the sound waves can provide energy to a physical reservoir computer microphone that the actual energy in the sound to power some of the system. You're always going to need a little bit of extra power from somewhere, but you can actually do quite a lot of powering of the system through some of its inputs. And especially if you've got accelerometers, because the whole system is moving around through in gravity, and that's a way of also accessing the gravity to help you power the system. And you also need some actuators. This is a robot, it's got to do something, it's got to be able to influence its environment. So you can have grippers and manipulators, sound production as well. Your robot can not only have an ear, but it can have a mouth. But also you need these actuators for controlling the internal dynamics. I showed you the actuators, the motors on the joints in the tensegrity device, but you can have pressure actuators as well, so sort of pneumatic systems and so on. And hierarchical control. I mentioned that the components, sort of the low-level modules themselves would still have some, potentially have some internal dynamics, and you can use a reservoir at the level of a module to help control that module. But then if you plug modules together, you can either have bigger reservoirs controlling the entire thing, knowing that the little subcomponents can control themselves, so that's a kind of a coarse-grained, higher level control. Or at some point, you might want to just have some top-down computation in there as well, if you really feel that you need that. But this modular hierarchical construction can give you distributed control, so that the individual legs know how to move, the individual joints know how to move. It's just reflexes, and then you only need to pass a small amount of information up through the system to the higher level top-down goals. They're not controlling every part of it. They're not micromanaging the system. They are just providing goals and so on. So I just want to finish off by saying what all I'm talking about here is the idea that you can use physical reservoir computing to build self-controlled robots that are using their own rich complex dynamics to provide not only their movements, but also their provide intrinsic computational ability, and that intrinsic computational ability can be exploited as the control system of the robot itself. So I'd just like to finish there. So thank you very much.
Thank you very much, Susan. It was impressive. So
thank you.
Thank you.
Eric, would you start?
Well, I don't know where to start because...
would you like me to start and then you come into the picture?
Well, let me just say one thing. It seems to me, okay, I can see where you can put a bunch of stuff together, have it interact, and do stuff. Basically, that's what you're saying, by having these interactions. The problem is, of course, that if you want to arrive at more complex tasks, in principle, it's impossible with such simple structures. Okay, unless, of course, you allow yourself to have randomness included, where you can view that also as a part of generating some structure. But if you want to generate a particular structure, in other words, a space-time event, you're going to need a hell of a lot more information than you've got in your interacting small parts.
Well, you can that's why I was saying about needing the levels of it. You can, so for example, the Taka robot that I showed, it does within itself have, it's using the dynamics of its parts, but it does have a little bit extra in there, of course, because that weight matrix, the output weight matrix, does have to be implemented somewhere. And that's the program, and that's the extra information that's over and above the pure dynamics of the internal reservoir. You've got those two components, but the reservoir is providing the information to the much smaller weight matrix. But there is something there.
I mean, I think it's very promising, and I think that's actually the way the human body works to a large extent. But
we still have this. Yeah,
we still have that the major monster that's up between our.
But nematodes do interesting stuff, and they don't have quite as much as this.
Yeah, sure.
Yeah.
Oh, okay, Gordana?
Yes, I was thinking about the connection between morphological computing. Can you explain for us? Because they are showing this passive walker and those things as morphological computing.
Yes. So that, I mean, it's related to that in the sense of what they're using is trying to just use the shape of the body itself to provide those dynamics, but they're having to design so those passive walkers are designed specifically to be passive walkers, and they can't actually do anything else. They can't turn around and walk back uphill. They can't skip and so on. But the idea here is it's taking those ideas that there's a kind of a natural intrinsic dynamics to these systems that can do some stuff, so that the control that you're then putting onto it isn't a micromanaged control of saying exactly how to do everything. It's just modulating the natural dynamics of the system anyway. So I think that's probably also answers Eric's question a little bit of where the extra information is coming from. It's not all coming just from the control system modulating the dynamics. It's because the body itself has got a natural dynamics of its own, and I'm not saying it's universal. I'm not saying that if you built this robot that you could then make it fly. You can't. It's not universal in the sense of it can only do what it can do, but you can modulate those things.
But I thought when I first looked at this stuff, which was just a few days ago, I thought that somehow the input to the weight matrix actually is related to the output. But somehow you're saying the input is random, has nothing to do with the actual output.
The input isn't random. The input's from the environment. The input weight matrix that distributes that input across the reservoir is random.
Okay.
Yeah.
In that sense.
Sorry,
So the encoding is random in the sense.
Yeah.
But the
Yeah, and what I find actually interesting about this is that although the maths that the underlying model says it has to be random, uniform random distribution, or whatever it is that you have, that makes the maths work. But actually, in practice, it doesn't have to be random. It can be relatively structured, because we got a bit confused when we started doing the physical reservoir material. Was clearly we had a thin layer of some carbon nanotubes. Clearly, there weren't connections between state points that are long distance apart and so on. So we did some experiments back in the simulated system, and instead of making it a random recurrent neural network, we kind of made it a grid recurrent neural network, and it still worked. And so actually, it doesn't need to be as random as the maths says. It's simply that just makes the analysis easier because you haven't got structure to it.
That may be related to the kind of output you're trying to achieve. So the same non-random structure may be totally useless in a different scenario.
Yeah. So again, what's interesting in reservoir computing is that it says to be random, but what everybody does when they're simulating it is that they They generate 100 random matrices and then choose the
Yeah, exactly.
which is no longer random, of course.
Yeah.
But that's why I said about also that you can have configuration voltages or something on your system, or you might tighten up your joints a bit in a robot and so on to make it a better computing system. So it's not completely random, but it's not completely ordered either.
Mm-hmm. Yeah. Could you say something about the higher dimensional space, this sort of mapping into this higher dimensional space, how that is, why this even works? I mean, I guess I'm trying to get my head around what you're doing, because I was thinking you had, in a different talk, talked about morphological development, okay? So, I thought, okay, you've got a genome, the genome is utilized to get the right kind of connections, and then you can maybe get a morphology on the other end, where the higher dimensional space basically maps the genome information into a much higher dimensional space, so it can be utilized in the development of the body. So,
okay, so that's a different project. I didn't talk about that project today. So I had a PhD student. He graduated just before Christmas, who was growing networks using a variety of techniques to start with a seed network, and then using a small neural net that's in every node, the same neural net in every node, to work out how to then grow. And that neural net can be trained. He was training it by evolution, not by backprop or anything like that. That neural network can be trained to give different properties to the system that finally grows.
Right. That would fit with your, and trained to have different kind of interactions to lead to different morphologies.
And it's not just, he wasn't using the networks that he was growing to be the morphology of a body. He was using the networks he was growing to be the random recurrent networks, random recurrent neural networks in a reservoir. So he was trying to grow good reservoirs.
Interesting.
May I ask more high-level questions for our interdisciplinary audience? Thinking about, you propose robots, and you propose this feedback loop, and we are seeing people implementing large language models into robotic bodies, and those robots starts to converge towards human behavior and human whatever. But if we imagine this coupling with the environment and the possibility to change its own morphology or its own function inside the body, how close can we ever get to the real living system?
There's so many things I want to say to answer that question. I'm trying to work out. First of all, the naive use of large language models is just things that are chatting. They're still hallucinating and so on. What I think is useful is those kind of models where, so many computer science algorithms, search algorithms, are generate and test. Evolution mostly, but there are various other search algorithms and so on, generate and test. The naive form of large language models, as far as I'm aware, are generate, and there's no test. That's why they hallucinate, because they just generate and go, "Whoa," and then it's not hallucination. You need to close the loop and put a test in and go, no, that one doesn't work.
Actually, some of them do that now.
And so, and as I understand it, and I'm not an expert on LLMs, but as I understand it, they're now putting them in a testing loop. Although the ones that I have seen, that testing loop is itself generative AI, so I still don't trust it. But if you could put it in a testing loop that was rigorous, like a proof checker or something like that, then I might be a bit more. But once you've got a generate and test, I saw a very interesting talk at the Artificial Life conference this year, last year, 2025 in Kyoto, given by Luke Steels.
Oh, look.
Yeah, and he and Takashi were using LLMs to implement Minsky's Society of Mind model, which I thought, actually, that's rather nice, because in Society of Mind model, the little components are not intelligent. That's the whole point. So I don't mind using unintelligent LLMs in that place. It was still hallucinating. They built a Society of Mind and put it in one of their robot heads and had it chatting to people in Venice, and members of the public were talking to it. And I might not have got the details right, but it was something like a member of the public asked it to recommend an ice cream place, and they said, "Oh yes, the best ice cream place is such and such," which was a good ice cream place, and it's on canal such and such, which it wasn't. So it was still hallucinating. But the thing that I think is interesting about that, from the point of view, is that they could then also listen in to the conversations the agents were having inside the robot's head between each other, because of course they were all LLMs and they were just talking to one another in natural language. So they could listen in to how the system was actually deciding to behave. And I think if you take something like that and add in a database of stuff that's true rather than hallucinated, and that it has to check itself against that, and can add stuff that it has discovered is true, I think then you're getting something very interesting could potentially happen. But that's intelligence. I'm not really interested in intelligence, because I think intelligence is overrated. I'm interested in the sort of the lower level computational abilities and how much we can do with a physical system without needing to be intelligent. And there's a lot, I think, that can be done there as well. But eventually, it's not going to be all physical reservoir computing. It's not going to be able to do everything. But it provides I think it provides a base level that can do a lot of the heavy lifting, so that the later brain doesn't have to worry about all the little details. I mean, when I'm walking, I can think and not worry about, I'm just automatically walking, because a lot of that is coming from the reflexes in my body.
But you've got a huge cerebellum.
Yeah, but I'm using that.
Which some say contains more neurons than the cortex. So,
yeah.
I mean, obviously, that's doing a lot of work.
It's maybe, but reflexes.
Maybe, come on.
Yeah.
Maybe our colleagues have comments.
Oh yeah, okay.
Pedro, do you have? I would be interested in Kate's comment, because I know her research. She might be coming with very interesting ideas. Kate, do you have comments?
Forgive me for joining late. I did not hear your talk. But from the little gist that I've gotten so far, I would, I think that the computational approach is really tapping into something important about the physical substrates, whatever they might be, the deterministic substrates, because they're really there. I think, there's pattern forming processes that are common. But when it comes to the living embodiment, I agree with Eric that it's really there's so much from the embodiment and the interoceptive senses that are all distilled through the cerebellum and all of that's where maybe there are going to be some processes that living systems are doing at a much, much deeper level that do contain a participatory information choice making piece. And and I'm an emotion researcher, and to my emotion is the one aspect of cognition that is uniquely embodied. It's uniquely personal. It addresses the identity defining and preserving and developing constraints that the body taps into and uses somehow. And we're real impressed with Mike Levin's work along those lines. So I would love to hear what I missed or how you get there. I think, though, that the computational approach is wonderful, because some of us have been talking about these things for a long time, and yet everyone's focusing on how to generate general artificial intelligence, and it's bringing us right up against these exact issues. So I'd love to hear what you're doing there.
Well, so I'm from the artificial life community, and there are two mantras about artificial life. One is, to think about life as it could be rather than life as it is. But there's also another mantra, which is artificial life is artificial intelligence from the bottom up, rather than trying to build a brain in a vat or whatever. Is actually to say, well, we can't even build an nematode or an ant or anything like that. Let's try there. But also, I did some work several years ago with a plant biologist who made me think about plants much differently, because normally with roboticists and artificial life and that, everything's an animal, isn't it?
Right.
But no. And of course, the higher level cognitive stuff is mostly to be able to move around and interact with the environment. And if you're stuck stationary, you don't need it. But plants don't have brains, but they certainly have behaviors, and they have responses, and so on. And I think actually, if we look more at thinking about, well, maybe we shouldn't be building intelligent robots, we should be building intelligent plants or artificial plants in that way that they can do various things. And so again, every time people start talking about intelligence and the brain and so on, I want to take several steps back and say, no, we can't even do very simple things. We can't do bacteria. We can't do plants.
Exactly.
We can't do all these things. Let's start there at something that we can at least understand if we're making progress there.
Indeed.
Thank you very much.
Yeah, it was very funny about intelligent plants. I think we call that agriculture. And we have been playing with it for millennia. I mean, all the plants we have domesticated and changed, etc. Well, in your talk, I was, in several occasions, I was reminded of Rodney Brooks. He was working in the 80s. Well, he continued.
Oh yes, Rodney Brooks. Yes.
Rodney Brooks. Yeah, because he was the bottom up versus the top down.
And subsumption architectures and stuff. Yeah.
Yeah, and I think you have taken a different angle, more computational, more close to disembodied bodies, so to speak. And I have found very tricky that you dismount the neural network and take the output. That's very cheating. So you develop a multi-use neural network by playing with the output.
Yeah. Well, I think that's quite interesting. Is that the training? It's what you think of the neural network isn't really the thing that you train. It is just sitting there wobbling away. Computationally or physically, depending on how you're doing it, and then you're just training the way you look at it.
Yeah.
So it's almost, as I said, it's like having you take this pair of glasses off and put a different pair of glasses on, and what you're looking at suddenly looks completely different because you've trained it for a different task. Or you could wear both pairs of glasses simultaneously and see it doing two different things. So it's it gives you an interesting perspective on what it means. Where is the computation happening? What's doing the computation?
I liked so much your picture where you show different organisms looking at the same world with the different optics. And that's the problem of observer in general.
Yeah.
And I don't know if you know of Umwelt. That's what's happening here.
Yeah.
It's extremely, I love it. Now I think I understood the main point.
But most of them have something in common. They have to achieve a life cycle.
Yes.
I mean, it is not a blind contact with the world, and that life cycle has base in similar structures, similar chemical components, DNA, enzymes, proteins, and all the metabolism. And so you finally see that the different glasses are more or less, it is sunglasses, normal glasses, and not so different. And we often don't pay attention that most, I would say all the biological information processing has just one goal. It is to propel. I think it was Spinoza was very elegant and was calling it the conatus principle, with the force of life to go ahead. And that's, I call it, for more clarity, let's say, it is advancing your life cycle. This is what moves our informational relationship. So we change the inputs, we change the outputs, depending on our internal engine. And this internal engine is quite intriguing and not well connected with the input-output schemes, I think.
Well, one thing that I'm confused about is that when you have these little animals in a circle, each with a different point of view and each with its own interface, but actually you're looking at little animals, each with its own neural structure and your particular view of that neural structure, whereas the way you actually use your network has nothing to do with its structure at all. That's because it's a random structure, and you're actually just using it to map your input into a higher dimensional space. So the image, it does not really cohere or coalesce with what you actually do.
It's a metaphor.
Yeah, exactly.
I'm moving. I mean, in particular, in that image, I'm moving the glasses onto the viewer rather than onto the reservoir. But the reason I like the metaphor is because it emphasizes that the computation is happening potentially in different places. Some of it's happening in the world, which is providing state and dynamics. Some of it's happening in the spectacles, whatever they are, and they will have evolved. And as you say, some of it's happening in the actual organisms that's using the output. But I use that metaphor to emphasize the fact that who is it who owns the output weight matrix? Is it the reservoir that has the output weight matrix as part of itself, or is it whoever's using the output decides to have the output weight matrix and use it to view the reservoir? And so it's not where you draw the circle around what's the computer depends on how you're asking the question, I think.
Yeah, maybe. The problem is, I guess we have to get to the point of how do you actually train this output, and where is the information coming from to train it?
No.
It's obviously not coming from the random network.
No. So in the classical case, when you're just using it, you've got a task you want it to do. So you've got some data so you can calculate an error function.
It captures a certain differential equation, and you're trying to model that differential equation.
No, well, yes, but you could be, but basically you're just sort of saying, I've got this. This is what my system is actually outputting. What weight matrix do I need to have there to get it to output what I want to see?
Yeah,
you just do that by you can do that by linear regression because it's only a linear output weight matrix. Yeah. And so again, with a lot of these things, everybody has the the sort of the base system that they describe as what's actually happening in the mathematical model of what's happening. And then when you actually do it for real, there's little tweaks that you have to add on. And
yeah, you do a lot of tricks and juggling.
Yeah. But I think it gives you a different set of tricks and juggling from classical top-down.
Yeah. Well, it's impressive the efficiency that you get. Now I'm wondering if you can generalize that efficiency to actually model a highly complex brain. Can we redo LLMs to be more in line with what you're doing? And then the problem comes, you've got huge complexity that you're trying to model. And that won't be doable by a simple one-shot method, I think. I don't know. I'm not sure.
Well, it'd be a very big one-shot method. Yeah. But also, I mean, classical neural nets, feed-forward neural nets are nothing like the way the brain works. So I'm not worried that reservoir computers might either, because...
But it is similar to the modularity that you talk about. You have these highly modularized, specialized parts of the brain. And then you got the role of white matter, which is just huge, which is not really investigated. And that may be something, I don't know, I'm just speculating, akin to your random network. Maybe not, obviously not. Oh no, it can't be because of the work by Werner and the disconnection syndromes.
This is nothing like a brain.
Yeah.
Either in scale or structure.
Yeah.
So
But much more relevant than Turing machine.
Yeah, you haven't got a tape in your head either. So
I didn't have time to touch a Turing machine model of computation because we are trying to learn to compute better.
Yeah,
that's the point. Oh, you can go with your new computational model till anything, but we must learn how to compute better.
And I think one of the interesting things is there's a lot of stuff saying, well, with reservoir computing, you can use physical material. You don't have to use, a classical digital computer to do it. Therefore, and then there's this huge leap. Therefore, we can do all these large, deep learning more cheaply. No, the scales we're talking about are very different. I think the killer app for physical reservoir computing is actually smart sensors. Let's go down much. The robot controller is more speculative because I thought it'd be more fun to talk about. But what I think the actual killer app's going to be is smart sensors, where you can combine the sensor and its computation in the same physical device. So a colleague of mine in Canada, Julian Sylvester, has done something interesting with MEMS devices. So the MEMS device is an accelerometer, basically. It's just a tiny thing that wobbles. But you can use the MEMS devices as reservoir computers, but you can also use the MEMS devices as sensors to sense acceleration. And so what you can do is you can combine these two processes to use essentially the same device. It's slightly more complicated than that, but essentially the same device to actually sense the input and then do some computation on it. So do a little bit of classification on it, all in the same device. And also, of course, the majority of the power for that is coming from the acceleration. So he's built a little system that he straps to people's legs to work out how they're walking, to do some for people whose gait isn't quite right and need some feedback on how to walk properly. But it's all being done in the same device. And so the idea that you can combine the sensing and some of the computation without having to do any A to D conversion, which is where you get a lot of problems, and without having to provide quite so much power, so you can have very low power devices that can be put out into the environment. I think that's where a lot's going to go. So if I was going to put money into physical reservoir computing, that's the area I'd put it into. But then a few generations later, we might have these smart robot controllers, but that's...
How exciting thinking about medical applications and those things in the future.
Yeah, can I make a comment? Like I said, I love what you're doing. The idea of putting the sensor and the computational bit in one unit is what nature has done, and it adds the third piece, the effectuator, the behavioral effector as well. So you have the sensor and the effector and the computational logic all in there. And that's what I talk about emotion as a sensory system, in that it delivers that basic valence of something that feels good versus something that feels bad, and moves the organism toward that which is beneficial and that which is yeah. So I think that's the piece, if that can happen. And I know Luke Steels, and we've talked about this. And yeah, there's a huge difference between the magic of large language models and what robots can do with sensors and effectors and world models, which is going to be closer to living systems. How much do you rely on the active inference approach, if you do at all? Not at all.
No.
Okay. Straight reservoir computing.
Yeah. For that, you know, I mean, I read about active inference. Is this the predictive coding stuff, or is that something different? Yeah. I mean, I think that's absolutely fascinating, but it's not something I know about. But it just feels, again, as a way of reducing the amount of computation you have to do, because you're only calculating differences and so on. But so yeah, but I've only read books about it. I haven't actually done any work on it.
Well, the difference is that it's all about model building and feed-forward prediction. Yet the training principles are still based on a gap between the model and the real-world fact.
Yeah.
And so what's missing there, you know, the reduction in energy, the reduction in surprise is the principle that all this magic is being built on. And that's great, but that's sort of what nature does too. But there's a valence. Surprises are good surprises, they're bad surprises. And that's, going to be the secret. But to me, the deep answers are hidden in the physics that we don't understand yet. But the quantum biology and the implications for sensory mechanics, like there really is some sense of acceleration in what we don't yet understand about gravity and rotational degrees of freedom and all of that. So there definitely is, I can't wait to see what you make of this and how you get from it. But I really think you're going to find yourself in quantum mechanics and the mysteries of all of that, and of course the inconsistency, well, the incompleteness and the indeterminacy, and perhaps some role for an agentic observer.
Everything's entwined with everything else. Yes.
I feel we are running out of time, and we are using Susan's time already after 7 o'clock. But Susan, can you say just a second?
I can stay a little bit longer. Of course, it's only just gone 6 o'clock for me. So
okay. If there are any other comments or somebody who wants to say something, Krasimir, do you have comments?
Yes, I have comments, but I think we are over the time. I will only show you the slides, and I will write a paper for more deep understanding what I mean. So I easily will say 3 sentences. I need to share my screen. to see what I prepare, but I will not talk in deep, only my conclusions. I hope you see my screen.
Yes.
Yes, this is one definition, maybe 30 years old, and first three paragraphs in red define regulation, and the last two define control. This is the main difference between these levels. So I need to go to my screen. Okay, I try to look to the physical reservoir computing through this lens and find some interesting strengths and limitations. So the key insight is physical reservoirs excel of how to move, but the question why, where, and for how long require higher level cognitive mechanism. So my conclusion is the reservoir computes brilliantly within a situation, but cannot reason about it. And this is a map of capabilities of self-control. So we have a lower level regulation, reactive operational control. So the high levels, we need more sophisticated system, more complex systems. So what is interesting is to study colony of reservoir computers like ants. So mechanism is very interesting, stigmatry and reinforcements. So for a more high level control, we need special kinds of memories and self models and metacognitions. This is all. Thank you.
Yeah. I don't disagree with any of that.
Yeah.
Yes. But, yeah, I think seeing you putting it down like that reminded me of Daniel Dennett's tower of different sorts of creatures, you know, going from just simply Darwinian and then Skinnerian and then Popperian and then Gregorian creatures. So I think that's, so, you know, they just evolve, or then they can learn, and then they can have their own mental model so they can predict. So anticipatory systems, and then the Gregorian is ones that you culture, so you learn from others. And I'm certainly here with these kind of levels, only thinking right down at the bottom. This is I use the word reflexes specifically for that. It's not reasoning.
Yes.
And again, I think that's why it's rather useful to talk of it as reservoir computing rather than as neural networks, because although the mathematical model is a neural network, it's got nothing to do with that kind of stuff. As you say, it's got no long-term memory, and in fact, it can't have long-term memory, and it won't work if it does. So, you know, planning and reasoning and so on is not what it's about. It's about modulating the dynamics of the system. So you might be able to use it to run, but you won't be able to use it to decide where to run.
Yes.
Thanks a lot, Susan and everyone. Pedro, what do you think? Shall we close the session? Do you have final words, something to add?
Who?
Anyone?
I think it's great to know that you're on the planet, Susan. Now I'm intrigued to look into the difference between reservoir computing, and hopefully there will be a video of this that I can look at.
It's
after
being
the
recorded.
fact.
Yeah.
Yeah.
Well, thanks everybody for such fascinating questions. That was I really enjoyed that. That's really great. Yeah.
We too.
Thank you. Thank you.
Great to see you all.
Susan, good to see you.
Especially you, Gordana.
Bye-bye.
Thank you again. Yeah,
Bye-bye.
very, very nice.
Thank you.
Okay. Sorry, there were little hands going up the screen. Thank you. Thank you, Faye.